On this section, we are going to use what we have learned on the previous section. What the fundamental theorem of calculus has done for us was to give us a way of evaluating integrals by using antiderivatives. That is, if we know the antiderivative of the functions that we're going to integrate. So this section, we're going to define the indefinite integral, and we're going to use a different notation for antiderivatives, and we're also going to talk about net change. The other thing that we're going to do is we're going to reformulate the second part of the fundamental theorem of calculus, so that it makes it a lot easier to deal with applications, which is ultimately the goal of calculus, is to be able to find different quantities that cannot be measured directly. So the first part can be rephrased in many ways. Potato, tomato, everything is the same. So we can also say that if we have a function that is continuous, then the antiderivative of this function could be named as the integral between a number to x of that particular function. And then the second part says that if I actually have a definite integral from one number to another number, then that can be found as the difference of one of the antiderivatives between those particular points. So this is very useful, and we're going to use a convenient notation for antiderivatives. Now, this notation right here is the one that we're going to be used for antiderivatives, and it's called indefinite integral. Now it's called indefinite integral because, as you can see, there is no upper or lower limit. So you are not expected to find the integral as a number. If I have the integral of f of x dx from 1 to 3, I know this is going to be some number, a quantity. But if I don't have any upper or lower limits of integration, then since we have said this is the antiderivative of f, then this is just gonna be some function. I don't know, I'm just gonna call it g of x. You can call it capital F of x. But this will be just a function. This is a number. So this is definite, and this is indefinite. So that's the difference. So on here, if we're saying that the integral of a function is the antiderivative, that means, or it is pretty much the same as saying that if I take the derivative of this antiderivative, I get the original function to begin with. So for example, the integral of x squared, I know it's x cubed over 3 plus a constant. And this is true because if I take the derivative of this side, I get back the function inside the integral. So remember that differentiating and integrating are inverse processes. So if I start with one and apply one of the processes, I'm going to get the other function, and then vice versa. So just to reiterate the fact that whenever I have limits of integration, what I'm ultimately finding is a particular number. And remember that that's the area under the curve. So what I'm finding is whatever the area is worth, or if I have a function that is positive and negative at the same time, what I'm finding is the sum of the sign areas. So just keep that in mind. If we're using definite integral, then what I'm going to have as answer is a quantity. Now it says whatever formula that you have, you can always verify it by actually applying the inverse process, which would be antiderivatives. So for example, the integral of secant squared, I know that is tangent plus a constant. Remember that these are antiderivatives. So for antiderivatives, I need the cherry on top because I'm talking about indefinite indefinite integral. But remember, if I'm using definite integrals, then the cherry on top will cancel out, so I really don't need it. So plus c is not needed on definite integrals, but it is needed on indefinite integrals. So anyhow, if you think that this formula is correct, then apply the derivative to this side and see if you get the function that is inside the integral. So you do know that the derivative of tangent is secant squared. So, and the derivative of a constant is 0. So you know that taking the derivative here gives you back this function. Looking at the table of formulas, this is on page 398, so please memorize them. There's a lot of them that you already have, since you already know the derivatives in general. So please do not forget to look at this, prepare flashcards or anything that you have to do this. Remember, if the function is being multiplied by a constant, the constant can come out outside of the integral. If you have the integral of a sum, then this is the same as the sum of the integrals. Notice how I can do the same for multiplication. So can't split the integral for multiplication, please, or division. They don't split. The only thing that I can do, if the function is multiplied by a constant, then bring the constant outside. But if it's multiplied by another function, then I can't do anything about it. I have to deal with the function the way it is. Now, just a little note, in functions where we have more than one piece to them, for example, remember y equals 1 over x, it has two pieces. So we have agreed that whenever we're using indefinite integral, then we just find one of the functions and we assume that that is applied to either the interval 0 to infinity or the interval negative infinity to 0. So this calculation would only apply to one of those intervals, and it's not like it's going to be over the 0, because the general antiderivative, it will have two parts, because it can be defined as only one part over the real numbers. We have to have one for less than 0 and bigger than 0, because that's where the break is. Now let's do example 1. There are some of the examples that are not printed out, but I would like to go over them because I think they offer a different things about what we're going to be working on. So it says find the general indefinite integral. So I know that I need the cherry on top because it's indefinite. So if you fail to put plus c, then you're going to have points taken. So please make sure that you do understand that you have to do that. Since plus or minus are the same, I mean minus is the same as plus and negative, so I know I can split these two functions. So this will be the integral of 10x to the 4th minus integral of 2 secant square of x. And you see how I made a mistake right now? I forgot the dx. If you're splitting into two integrals, then both of them should have a dx at the end, both pieces. Now I'm going to apply the property that says if a constant is multiplying the function, the constant can come in front. So this will be 10 times the integral of x to the 4th dx minus, and then the 2 can come outside, 2 integral secant square of x dx. Now I'm going to look at my formula paper and I'm going to find what these functions are talking about. So this is a power of x, so I'm going to apply this. So this will be 10 x to the 5th over 5. And then I have minus 2, and then this one is right here, so I know it's going to be tangent of x. Since this came from the integral of one single function, I only need to write the constant once. I don't need two different constants for each piece. So after you have finished integrating, I know you need a cherry on top, but you only put it once, because this constant will include the constant from here and the constant from here, so why bother distinguishing between two constants? We're dealing with the same function, so one constant is enough. Now the only thing to do will be to simplify. I know I can simplify 10 and 5, so this would be 2x to the fifth minus 2 tangent of x plus c. And that will be the final answer. Remember that this integral will give you a function in return, a family of functions actually, because it's going to be this function plus a constant, and you know that you can have any constant in the real number world, so this is going to give you a family of functions. You can have this antiderivative, you can have it in many ways. As soon as you do vertical translations, you can move it up or down. So we have seen that before. Now in example 2, there is a little bit of work to do before using the table, because this function right here is not on my table, so I'm gonna have to do a little bit of converting in here. So remember that the way this is written, that means sine of theta times sine of theta, because that's what it means, sine of theta squared, and you have cosine of theta. Now every time you have sine over cosine, you have tangent, but if you have cosine over sine, then you have cotangent. Now what is left is a sign that is below the division line, so this is like having the reciprocal of sine. The reciprocal of sine is cosecant. So this expression can be rewritten as integral of cotangent of theta, cosecant of theta, d theta. Remember that we're going to have a d something at the end. If we're talking about t, this would be dt. If we're talking about theta, this would be theta. So hopefully I'm going to have that function in my table. So I'm looking for cotangent, cosecant. Multiplication is commutative, so this is cotangent, cosecant, cosecant, cotangent, and the integral will be negative cosecant of theta. This is x, but I'm not dealing with x, I'm dealing with theta, so you must put theta plus the cherry on top, and then I'm done. Now in example 3, it says evaluate. So the word is implying that the answer is going to be a number. Not only that, but also you see there are limits of integration, so that is another hint that you're going to have to evaluate and get an answer. This is not indefinite, this is a definite integral. So keep those differences in mind. So my answer is going to be a number. So since it's the integral of a difference, I can split integral between 0 to 3 of x cubed dx minus integral between 0 to 3 of 6x dx. Now this is, I'm going to apply the power rule here, but backwards, so it's going to be x to the 4th over 4 evaluated between 0 to 3 minus, and then the 6 can come in front, and then x will be x squared over 2, and I'm going to evaluate that from 0 to 3. Now you have to be careful when you do the minus a function right here. Please keep some parentheses. I want to show you how. So I'm going to evaluate here, so I have 3 to the 4th divided by 4 minus 0 to the 4 divided by 4 minus, please put some bracket or some parentheses just to make sure that you are minusing the quantity of here. So 6 divided by 2 is 3, so it's 3 times x squared, which will be 3 squared first, minus 3 times 0 squared. this in here would be 81/4 minus this in here will be 27, and then this fraction minus 27 is negative 6.75. And now this should ring a bell because we've done this in example 2 on section 5.2. So now we have a system to do that without sums or anything crazy like that. And then we have example 4. I'm finding the integral between 0 and 2 of this function, and then we're going to interpret this in result in terms of the areas. Now this function is sketched right here, and between 0 and 2 the area under the curve will be this area. Now I know that it says under, and the word under will apply as long as the function is positive, because under the function is this, under the function is this. But when the function is below the x-axis, this is not actually under, this is above the function. But in general we say the area under the curve, or the area under f. But it's always, the shading is always against the x-axis. So it's not like under, because then we will never be able to finish that shading. So under implies from the function to the x-axis always. Okay, so right now I can see how I need to split this integral. So this is the integral between 0 and 2 of 2x cubed minus integral between 0 and 2 of 6x plus integral between 0 and 2 of 3x squared plus 1 dx. What am I forgetting? The dx everywhere else. Okay, so now that's done. The 2 can come in front, so the integral of x cubed is x to the 4th over 4 evaluated between 0 and 2 minus, again I have the integral over here on the previous step, so I know that that's 3x squared. 3x squared between 0 and 2 plus 3 from 0 to 2 of 1 over x squared plus 1 dx. This is not a power of x, so I'm pretty confident that I'm going to be able to find some formula here. And I have it right here. The integral of 1 over x squared plus 1 is arctangent of x. But because it had the 3 in front, I needed to acknowledge that 3 is the same as 3 times 1, so I can bring the constant outside the integral by properties. Now 2 and 4 simplify, so this will be 2 to the 4th divided by 2 minus 0 to the 4th divided by 2 minus, please put this entire thing between parentheses, 3x squared evaluated at 2 minus 3/0 squared plus, I know that this is going to be 3 arctangent of x between 0 and 2. And now let's simplify this. This is 2 cubed, which is 8, minus this is 4/12 minus 12 plus the 3 times arctangent of 2 minus arctangent of 0. Now I know arctangent of 0 is 0, so the actual value of this definite integral is a minus 2 is negative 4 plus 3 arctangent of 2. Now this is the exact value, and that will be the end. If this was a function about something else in particular and you needed some approximation, then you need a few decimals. 4 or 5 are fine. So an approximate value is negative 0.67855. Remember, arctangent is on the calculator, and your calculator should be on radian mode. Okay, I don't think we're going to see any degrees, so please make sure you do always check that, otherwise you will get a different answer. Okay, so let's talk about what the interpretation is. This integral between 0 to 2 is the sum of the sine areas, meaning it's not the sum of all the areas, because as you can see you get a negative number, so areas are not negative, but this area is going to have a positive sign in front, and so will this one, just because they are above the x-axis, and this area will have a negative sign in front because it's below the x-axis. So since the integral is a negative number, that means the area below the x-axis won. There is more area in here than these two pieces combined. And actually the areas are close because the difference is less than 1. I mean, not really close, but you can see visually that they are almost the same, but actually the negative area in here won. So it's the sum of the sine areas. The area below the x-axis is greater than the sum of these two pieces above the x-axis.